Okay, so we're going to look at a couple of examples of solving second-order equations with constant coefficients. Now, the trick for constant coefficients is that we're going to assume a solution that has a particular form, which in this case is y equals e to the rx. And the reason for this is because when you take the derivative of e to the rx, you just get a constant multiple of the original function. You get r times e to the rx. And if you take the derivative again, you also get a constant, in this case r squared, times the original function. And so that's capable of satisfying this differential equation where the derivatives also only differ by a coefficient, by a constant. And this is the solution form that we're always going to use anytime we have higher order equations. In fact, not just second order, but any higher order equations where the only function of x that's being multiplied, or function of t, being multiplied by each of the derivatives is just a constant. If we make our substitution into the original equation, r squared e to the rx plus 3 times r e to the rx minus 54 e to the rx. What we end up with is an equation where there's an e to the rx in front of every term. And so if we factor that out, 3r minus 54 equals 0. And e, the exponential function, can never be 0, and so we're left with the characteristic equation for this differential equation, which is this polynomial in R. And it's called a characteristic equation because basically if you just pull off the coefficient of y double prime and you make it the coefficient of r squared, and the coefficient of y prime and you make it the coefficient of r, and the coefficient of y and you make it the constant, that you get the same, basically the same equation. And so it's characteristic in that sense. When we looked at Cauchy-Euler equations, we saw that we got a slightly different equation. This middle coefficient had to be modified by subtracting 1, and so that was an auxiliary equation, but this is considered characteristic. And in fact, we'll get the same equation if we use systems of equation methods, which we're not going to do here. To find a solution by that method, we will also end up with the same equation because this is related to the eigenvalues. But that's for a different video. So what we need to factor. All that factoring you learned how to do in high school. This was the reason that you learned how to do it. So what are our factors of 54, which have a difference of 3? We're going to say 9 and 6. And the larger one has to be positive because when you add them, you get a positive answer. And so our two roots are going to be -9 and +6. And so we're going to get two solutions. E to the -9x and y2 is e to the 6x. And so our final solution, y of x, is going to be c1 e to the -9x plus c2 e to the 6x. And we can verify that these are in fact independent solutions that satisfy the equation by calculating our Wronskian. E to the -9x, and then this becomes -9 e to the -9x, and up here we have e to the 6x and 6 e to the 6x. And when we multiply these, we get e to the negative 3x, 6 e to the negative 3x, plus 9 e to the negative 9x, negative 3x, because negative 9 and positive 6 add to be negative 3. And so we end up with 15 e to the negative 3x. And of course, keep in mind that is related using Abel's theorem to our original coefficient up here in the equation. The exponential e, it has the negative sign flipped, give or take a constant. And of course, this constant will be negative of what it is if we switch the order of our two functions. This is never 0, and so we know they are, in fact, independent. And we could verify that this is, in fact, a solution to the differential equation by taking our two derivatives and plugging them into our function. And then if we had initial conditions, we would then be able to solve for C1 and C2.